Hey everybody, here are the notes for homework number 17, part 1. It's called Trig Identities, but I think the more appropriate title is the unit circle and trig identities. So we're going to talk about the unit circle for a minute here. And we're going to do this by talking about finding sine, cosine, and tangent of pi over 6 radians. So the idea here is that for pi over 6 radians, which is one of our special angles, we could draw the special triangle. Right? We could draw, the angle pi over 6 here, pi over 3 here, and the sides are opposites 1, hypotenuse is 2, medium angle, medium side, root 3. But we could also use any multiple of this triangle, also called a similar triangle. So if I multiplied all of the sides of this triangle by 1/2, 2 times 1/2 is 2, sorry, 2 times 1/2 is 1, 1 times 1/2 is 1/2, and root 3 times 1/2 is root 3 over 2. And we could use this triangle, and the reason I want to use this triangle is because this triangle has a hypotenuse of 1, which is going to correspond to the hypotenuse here being 1 or the radius of the circle being 1. So in this triangle, the adjacent side is the square root of 3 over 2, and the opposite side is 1/2. But, and let me zoom in here a bit because I feel like I want this to be easier to see here. If I go over root 3 over 2 and up 1/2, these are the coordinates of the x coordinate is root 3 over 2, and the y coordinate is 1/2. What I also want to point out is that we already know from this triangle or this triangle that cosine, I'm going to do cosine first here, cosine of pi over 6 is the adjacent over the hypotenuse, which is the square root of 3 over 2. And sine of pi over 6 is the opposite over the hypotenuse, which is 1 over 2, or over here, 1/2 over 1, which is 1 over 2. And just for the sake of somewhat completeness, tangent of pi over 6 is the opposite over the adjacent, which is 1 over root 3, which is root 3 over 3. I'll also point out that we could have gotten that by, well, and also, so what I really, really want you to see is that the xy coordinate here, the x coordinate really is just cosine of the angle, and the y coordinate really is just sine of the angle. So we could definitely think of this as being equal to the x coordinate of cosine of pi over 6 and the y coordinate of sine of pi over 6. So, say that again. Notice that the xy coordinate on the unit circle, like the circle of radius 1, is just root 3 over 2, comma 1/2, aka cosine of pi over 6, comma sine of pi over 6. That was not a, excuse me, that's not a coincidence. And so, more generally, this idea holds. If theta is the angle of interest measured from the positive x-axis counterclockwise, so we're going this way. So if theta is the angle of interest in a unit circle, then the xy coordinate on the unit circle is the coordinate cosine theta, comma sine theta. And it's exactly because if you look at this right triangle, cosine theta is equal to the adjacent over hypotenuse, which is x over 1, which is just x. And sine theta is the opposite over hypotenuse, which is y over 1, or just y. I will point out that we can extend all the other trig functions using this idea as well. So we can say that sine of theta is y, cosine of theta is x, and tangent of theta is the opposite over adjacent, which is our y over x. So if we knew the y and the x coordinate only, we could say that tangent of theta was just y divided by x. So like that previous problem where I said tangent of pi over 6 is 1 over root 3, I could have just looked at these coordinates. That's the y, that's the x. I could have said, oh yeah, tangent of pi over 6 is the y coordinate divided by the x coordinate. And then I can flip and multiply and get 1/2 times 2 over root 3, which is 2 over 2 root 3, which is 1 over root 3. And you can rationalize and get root 3 over 3. So as long as you know the xy coordinate of the point on the unit circle, you can find sine, cosine, and tangent, and all the reciprocals. Cosecant is going to be 1 divided by y. Secant is going to be 1 divided by x. Cotangent is going to be x divided by y. Because again, cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. All right, so what we're going to do with this is we're going to say, well, great, that's true for any point on the circle. We were doing that kind of in the last class where we were drawing like the triangles in different quadrants, but there's actually a very specific reason we want to think about this. This specifically allows us to find the trigonometric functions of quadrantal angles, which are angles that terminate on the x-axis or y-axis. So for example, 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, or anything like 450 or right, any like really big angle measure, which is just going around and around the unit circle. Like if I said 720 degrees, that's still a quadrantal angle because it terminates on the x-axis. In radians, same idea, 0 radians, pi over 2, pi, 3 pi over 2, 2 pi. So we're going to use the unit circle to evaluate the 6 trigonometric functions of theta equal to 90 degrees. I'll point out that on this unit circle, I'm actually going to fill in all this stuff here. So the radius is 1. To the right here, this angle is 0 degrees or 0 radians. Up here, this angle is 90 degrees or pi over 2 radians. Over here to the left, this angle is 180 degrees or pi radians. Down here, it's 270 degrees, just increasing by 90 degrees each time, or increasing by pi over 2 radians each time. And finally, this is also, if you go 1 for revolution, 360 degrees or 2 pi radians. So for net, oh, and then also the points. So I'll remind you, this is a circle of radius 1. So if you go from 0, 0, 1 to the right, your y-coordinate's still 0 and your x-coordinate's 1. If you go from 0, 0, 1 up, your y-coordinate's 1 and your x-coordinate is 0. If you go left, your y-coordinate's 0, your x-coordinate's 1. You go down, your x-coordinate's 0, your y-coordinate's -1. And I said -1 here, right? And then that's our x and that's our y-coordinate. So this is, right, this point here is literally equal to cosine of 0 radians, comma sine of 0 radians. So cosine of 0 is 1, sine of 0 is 0. Or to answer the question, 6 trig functions of 90 degrees, well, cosine of 90 degrees is equal to the x-coordinate there, which is 0. Usually I do sine first though. So sine of 90 degrees is the y-coordinate, which is 1. Tangent of 90 degrees is going to be a problem. Tangent of 90 degrees would be the y-coordinate divided by the x-coordinate, which is 1 divided by 0. But division by 0 is undefined. So we would say that tangent of 90 degrees does not exist or is undefined. And then the reciprocals, cosecant of 90 degrees is 1 divided by 1, which is 1. Secant of 90 degrees is going to be 1 divided by 0. But again, division by 0 is a problem. That's going to not exist. And then finally, cotangent of 90 degrees is going to be, instead of 1 divided by 0, it's going to be 0 divided by 1. 0 divided by 1 is just 0. So sine is 1 and its reciprocal is 1. Cosine is 0 and its reciprocal doesn't exist. Tangent doesn't exist and its reciprocal is 0. Let's do one more like this just to get a kind of idea of what the pattern is, and then I'll say some more to the pattern. So use the unit circle to evaluate all 6 trig functions of theta equal to pi. So when I do this, I almost always draw the unit circle with what I like to call, my wife hates this, the 4 corners of the unit circle. I know the circle doesn't have corners, but it's easier than saying other things. So this is the point 1, 0, 0, 1, -1, 0, -1. And my angles are 0 radians, pi over 2 radians, pi, 3 pi over 2, 2 pi. So in this case, I'm looking over here at pi radians where the angle, where the point is -1, 0. And again, I know that the x-coordinate is cosine of my angle. The y-coordinate is sine of my angle. I always think about it being alphabetical. X comes before y, and cosine starting with the letter C comes before sine starting with the letter S alphabetically. That's one way to remember which one is which. Cosine before sine, x before y. But then we write sine first, super annoying. Sorry. So sine of pi is going to be 0. Cosine of pi is -1. And tangent of pi is 0 divided by -1. This is one of the reasons we write this way. So you have sine over cosine. So then you can just do the y divided by x to give you tangent. And 0 divided by not 0 is 0. And then we take the reciprocals. Cosecant of pi, you could either just think of taking 1 over 0, which is can not exist, or you could think of, right? No, it's just easier that way. You can either be 1 over the y value, which is still 1 over 0. So I like just writing does not exist if you know it's going to be 1 over 0, right? It would have been 1 over 0. Does not exist. Cosine of pi is -1. So secant of pi, the reciprocal of cosine of pi, is going to be 1 divided by -1, which is negative. And then lastly, cotangent of pi is the reciprocal of tangent, which is going to be -1 over 0. Oops, that's a does not exist. So here's how this always ends up going. Of your sine and cosine, one of them will be 0 and one of them will be either +1 or -1. Of your cosecant and secant, one of them will be the same as whatever its reciprocal was. Like, so if cosine was -1, secant will also be -1. Or if in the previous one, sine was equal to 1, cosecant is one of them, which is also 1. Sorry, I said if sine was 1, cosecant is also 1. And then whichever one of those is 0, the reciprocal will not exist. And then for tangent and cotangent, one of them will be 0 and one of them will not exist. It always works this way for these quadrantal angles, where it's either 90 degrees or 180 degrees, or 170 degrees, or 2 pi radians, or whatever. On these things, on these angles that are the 4 corners of the unit circle, the quadrantal angles, you always get 2 zeros, 2 either -1s or +1s, and 2 does not exist. Always. All right, so that's finding trigonometric functions of quadrantal angles. Let's look at some trig identities. There are some identities we already kind of know. So tangent to theta, we just talked about how it was y divided by x. You can also think of it as sine theta divided by cosine theta. These are called the quotient identities, which are just fractions. Cotangent to theta is the reciprocal of tangent, so you can think of it as the reciprocal of sine theta over cosine theta, which is cosine theta over sine theta. Secant of theta is the reciprocal of cosine, so that's literally 1 over cosine. And cosecant of theta is the reciprocal of sine, so literally 1 over sine. These are the ones you probably need to know the most. There's technically a few others, which I will point out. So also, although these are less used, tangent of theta is 1 over cotangent of theta, or the reciprocal of cotangent. Cotangent theta is the reciprocal of tangent. And we can also write that cosine of theta is the reciprocal of secant, and cosecant of theta is the reciprocal. Oh, sorry, I wrote that one. Sorry, apologies. That sine of theta is the reciprocal of cosecant of theta. But usually when you're trying to simplify an expression using identities, you're starting with something like this and replacing like tangent with sine or cosine, or cotangent with cosine or sine. We don't often replace 1 over secant with cosine. We just kind of read it as 1 over 1 over cosine. So these 4 are the 4 important quotient identities. These other 4 are less often used. Then we have the Pythagorean identities, which have to do with the Pythagorean theorem. So I'll point out in this triangle, we have the Pythagorean theorem says that x squared plus y squared is equal to 1 squared, but 1 squared is just 1. But I'll remind you, we just said that the x coordinate was the same as cosine theta, and the y coordinate was the same as sine theta. So really, it would be appropriate and correct to write that x squared, or cosine squared, plus sine squared, or y squared, is equal to 1. And this is what I have to refer to as the most famous trig identity. Cosine squared theta plus sine squared theta equals 1, or sine squared theta plus cosine squared theta equals 1. Let's see, do I have? Yeah. I'll just point out it's true for any angle. So just for example, for an angle we know, if I picked, say, theta equal to 5 pi over 6 in quadrant 2, I know the reference angle is pi over 6. Looks something like this. So I know that cosine should be negative and sine should be positive. So cosine of 5 pi over 6 is going to be negative root 3 over 2. Thinking about the triangle, right? It's a 1 there, a 2 there, a negative root 3 there. And then sine of 5 pi over 6 is going to be positive 1/2. And so then if I do cosine squared of 5 pi over 6 plus sine squared of 5 pi over 6, I end up getting, well, cosine is negative root 3 over 2, so I get negative root 3 over 2 squared plus 1/2 squared, which is equal to negative square root of 3 squared is 3, 2 squared is 4, 1 squared is 1, 2 squared is 4, and 3/4 plus 1/4 is 4/4, which is equal to 1. Checks out. There are two other ways of writing this identity. So you can either subtract cosine squared from both sides and write sine squared theta is equal to 1 minus cosine squared theta. It's an alternate version of the same identity. You could also subtract sine squared from both sides and write cosine squared theta equals 1 minus sine squared theta. There are two other Pythagorean trigonometric identities. They can be found in a couple of different ways. Just trying to think about the best way I would want to show it. Yeah, so typically what we do is we take this first identity and divide each thing by either cosine squared or sine squared. So if we divide by cosine squared, we end up getting cosine squared theta divided by cosine squared theta plus sine squared theta divided by cosine squared theta equal to 1 divided by cosine squared theta. Anything divided by itself, as long as it's not 0, is 1. So like 5 divided by 5 is 1. Cosine squared divided by cosine squared is 1. 0 divided by 0 is, okay, it's a problem. We're not there. So this is going to be 1. Sine squared divided by cosine squared is the same as sine theta divided by cosine theta, quantity squared. And 1 over cosine squared is the same as 1 over cosine, quantity squared. But sine divided by cosine is tangent of theta. So it's going to be tangent squared theta. And 1 divided by cosine is secant theta, so it's going to be secant squared theta. So there's another Pythagorean trig identity. 1 plus tangent squared theta equals secant squared theta. Or as a student said to me one time, and I've never forgotten it, I tan and get sexy. Unforgettable. Very memorable. The other Pythagorean trig identity, which is similar, is instead of dividing everything by cosine squared, we divide everything by sine squared. We divide by sine squared. So over again. So I'm gonna actually write it instead of as cosine squared plus sine squared, I'm gonna write it as sine squared plus cosine squared, but it shouldn't matter which order we add things in. So we have sine squared theta plus cosine squared theta equals 1. And if we divide everything by sine squared now, we end up with 1 plus cosine divided by sine is cotangent, so it's going to be cotangent squared theta. And 1 over sine is cosecant, so 1 over sine squared is cosecant squared theta. This one gets used less, but it is still a perfectly good trigonometric identity. And then sometimes you could write this as tangent squared theta equals secant squared theta minus 1. It's less often. And similarly here, you could say cotangent squared theta equals cosecant squared theta minus 1. So these are all your Pythagorean trig identities. You've got your kind of your original versions. This guy here, this guy here, this guy here. And then you've got your alternate versions. These guys here. These guys here. All right. We're going to use these all in a second. One more type of identities. We have the double angle identities, which are kind of weird, but we'll show some how they work. So there's a double angle formula or double angle identity for sine of 2 theta. So it's like sine of 2 times an angle, and it's equal to 2 times sine of the original angle times cosine of the original angle. We'll do an example of that in a second. There's a similar but different formula for cosine 2 theta. Cosine 2 theta is equal to, or cosine of twice theta is cosine squared of theta minus sine squared of theta. Careful, don't confuse this formula with the trig identity we just talked about, right? The other trig identity was cosine squared theta plus sine squared theta equals 1. Whereas this one is cosine squared theta minus sine squared theta equals cosine of 2 times theta. Very different. They look very similar. So we're going to find sine of 2 times 30 using the double angle formula. And then we'll also use the special triangle. Actually, let's draw the special triangle first. So here's my special triangle. 60 degrees. The other angle is 30 degrees. Right angle here. Opposite 30 is the small side. Opposite 90 is the biggest side. Opposite 60 is the medium side. So using the double angle formula first, sine of 2 times 30 degrees should equal 2 times, sorry, you can't see it, 2 times sine of 30 degrees times cosine of 30, which is equal to 2 times, let's see, sine of 30 degrees is opposite of hypotenuse. And cosine of 30 degrees is adjacent of hypotenuse. 2 times 1/2 is just 1, so that's 1 times root 3 over 2, which is just root 3 over 2. On the other hand, if I just look at sine of 60 degrees kind of the more normal way, 60 degrees is right there. Sine is opposite over hypotenuse, which is root 3 over 2. So they match. All this does is show us that it is actually correct to use this double angle formula, right? It's always true that sine of double one angle is equal to 2 times sine of the original angle times cosine of the original angle. I have something over here. Yeah. So for example, no, I don't want that example. Right, if someone said like find 2 times sine of 22.5 degrees times cosine of 22.5 degrees, I would say, oh, that's the same as sine of 2 times 22.5 degrees. I'm using the identity, and then 2 times 22.5 degrees is 45 degrees. And we know that sine of 45 degrees is root 2 over 2. So that's kind of the idea of a problem like that. In a similar way, we can use the double angle formula for cosine to show that it also works. So cosine of 2 times 90 should be equal to, according to the formula, cosine squared of just 90 degrees minus sine squared of just 90 degrees. Going back to the unit circle with the quadrantal angles, 90 degrees is up there, and the point there is 0, 1, so we know that cosine is 0 and sine is 1. That's going to be 0 squared minus 1 squared. Be careful here, the 1's getting squared before it's getting subtracted. That's 0 minus 1, which is just negative 1. Or we could find cosine of 180 degrees by looking at 180 degrees, which is over here, and the point there is negative 1, 0, and oh yeah, cosine of 180 is negative 1. Same answer either way. Okay. So kind of like I already did, use an identity to evaluate cosine squared 15 degrees plus sine squared 15 degrees. Well, this one we actually don't need to really do anything because we know that cosine squared of an angle plus sine squared of an angle is always equal to 1. Because cosine squared of theta plus sine squared of theta is equal to 1 for any angle theta. Always true. That's why it's called an identity, because it's always true. This next one's a little bit more work. Use an identity to evaluate cosine squared 15 degrees minus sine squared 15 degrees. So this is where we can't just say it's equal to 1, right? It's not a Pythagorean identity. It's a double angle identity. So we know that cosine squared of theta minus sine squared of theta is equal to cosine of 2 times theta. So in this case, our theta is the 15-degree angle. So it should be true that this is equal to cosine of 2 times 15 degrees. But we know what cosine of 30 degrees is, right? We draw a 30, 60, 90 triangle. Opposite Opposite of 30. So cosine of 30 should be root 3 over 2. That's how we do that. Oh, sorry, you couldn't quite see my triangle. Apologies. My 30-degree angle, the opposite of the 30-degree angle is 1, the opposite of the right angle is 2, and the opposite of the medium angle is 3. And use the adjacent over the hypotenuse to find the cosine of 30 degrees. 2 times 15 degrees is 30 degrees. All right, last part of this section, simplifying some trigonometric expressions. So this often involves writing all trig functions in terms of sine and cosine, using the quotient identities, and then using a Pythagorean identity after that. Not always, but those are usually the best. So here, the first thing I would probably do is rewrite cosecant and cotangent in terms of their sines and cosines. So I'm going to rewrite this as 1 minus cosine of x times cosecant, which is 1 over sine of x, minus cotangent, which is cosine of x over sine of x. In this case, it happened we got lucky because the right-hand piece of this, or factor, those have a common denominator. So I could actually rewrite this as 1 minus cosine x. So that's supposed to be 1 plus cosine x. I'm so sorry. There was a mistake here somewhere. Or actually, no, sorry, this was supposed to be a plus here. Apologies. There, much better. So it's going to be 1 minus cosine x times the fraction 1 plus cosine x over sine x. And although you could skip this next step, I think it might be worth seeing. We can think of 1 minus cosine x as just 1 minus cosine x over 1 times 1 plus cosine x over sine x. We're going to have to FOIL the 1 minus cosine with 1 plus cosine. I'll point out that these are conjugates. We multiply conjugates, the middle terms are canceling. You can still write it out though. 1 times 1 is 1. 1 times cosine is cosine. Negative cosine x times 1 is minus cosine x. And negative cosine x times cosine x is negative cosine squared x. All divided by 1 times sine of x, which is sine. And look, the middle terms, the cosine x and the negative cosine x cancel out. So we get 1 minus cosine squared x all over sine of x. But then, there's a trig identity. 1 minus cosine squared x is equal to sine squared x divided by. The sine squared divided by sine is just sine. And that's our simplified answer. So look, this very kind of ugly looking thing up here, 1 minus cosine times cosecant plus cotangent, simplified all the way down to the single trigonometric term, sine of x. That's kind of the idea with simplifying these trigonometric expressions using identities. Let's do another one. Cosine x divided by cosecant x minus sine x. Okay, so again, I'm almost always a fan of starting off by rewriting every trig function in terms of sine and cosine. So I'm going to rewrite cosine of x over cosecant of x minus sine of x as cosine of x divided by 1 over sine of x minus sine of x. And then, since I have fractions in my denominator, I'm going to get a common denominator of those fractions. I'm going to say that this is sine of x over 1. I'm going to multiply that by sine x over sine x. So then I can rewrite this as cosine x over 1 over sine x minus sine squared x over sine x. And now we have a common denominator in our denominator. So we can rewrite that as still cosine x on top over 1 minus sine squared x all over just sine x on the bottom. Now that we've got a single fraction in the bottom, we can flip and multiply. So we can think of this as cosine of x times the reciprocal of the bottom. So it's sine x over 1 minus sine squared x. But 1 minus sine squared x is a trig identity. That's another Pythagorean identity. It's really the same as cosine of x times sine of x divided by cosine squared of x. And you can think of the canceling of cosine there, or if you really wanted to, you can think of this as cosine over 1, multiply out the top and the bottom. So it's cosine x times sine of x over cosine squared x. If you don't just want to cancel a cosine on the top and cosine on the bottom, you can even do one more step and write it as cosine x times sine x on the top. And cosine squared of x just really means cosine x times cosine x on the bottom. You can definitely cancel or divide cosine by cosine to get 1. So we're left with sine x over cosine x, which is equal to tangent of x. Sometimes I write a parentheses, sometimes I don't. I usually like the parentheses just because it kind of will indicate you're taking sine of something, cosine of something. There always should be something inside the parentheses when you're writing sine of a thing or cosine of a thing. Just like the natural log, just like the square root, there always has to be an argument inside your function. One more of these, and then we will stop this video and record one more short one after this. Simplify cosine x times cotangent x plus tangent x. So again, the usual first steps. Rewrite your trig functions in terms of sines. Oh, sorry. Simplify cosine x times cotangent x plus tangent x. I'm going to rewrite cotangent x as cosine of x divided by sine of x. I'm going to rewrite tangent of x as sine of x divided by cosine of x. I am going to get a common denominator inside here. So I'm going to write this as cosine of x. Thinking about how you could distribute it, but no, let's do it this way. So I'm going to write this as cosine of x over sine of x times cosine x over cosine x. And similarly, this is going to be sine over cosine x over cosine x times sine x over sine x. That'll give me a common denominator. So now I have cosine x times cosine is cosine squared x over cosine x sine x plus sine squared x over cosine x sine x. But now that there's a common denominator, I can put those together with one fraction. So the cosine x times cosine squared x plus sine squared x all over cosine x times sine of x. But that's really cosine of x times cosine squared x plus sine squared x is our most famous trigonometry. That's just equal to 1. The bottom is still cosine x times sine of x. But then we can cancel a cosine here and a cosine here, at least we could have done that a while ago, and get 1 over sine of x, which we should then write as cos. Not the answer here. All right, that is the end of homework numbers, the notes for homework number 17, part 1.